So I want to continue on with the Rayleigh number. In the previous lecture, we looked at, we derived the Rayleigh number for a bottom heated system. That would be like the Earth's mantle. At the very bottom is very hot and the top is very cold. We might actually consider another scenario which is not bottom heated, but instead you have heat production inside. This is from uranium, thorium, and potassium, which radioactively decay and generate heat. And so it's generating heat from the inside, which may actually cause reduce the thermal contrast at the base. And you may not get a boundary layer as we know it down at the bottom of the mantle, okay? And so when we derived the Rayleigh number, we played this game of considering a spherical blob that had a density contrast relative to the mantle. Here it has a radius r, relative to the surrounding mantle that scales with the temperature difference, right? So that's density times thermal expansion coefficient times the temperature contrast between the blob and the hot blob and its surroundings. And we did a force balance, like a Stokes rise velocity, and we calculated the rise velocity. We looked at the time scales of how fast it would rise and compare that to how long this blob would cool off conductively to the point that it had no thermal buoyancy. And that's, when we compared those two time scales, and that's how we got the Rayleigh number. Now, we could consider this case if the reason why this thing is hotter relative to its surroundings is because it is undergoing internal heat production, right? Due to potassium, uranium, thorium decay, okay? And we're going to call that internal heat production H, which has units of watts per kilogram, right? Or this is joules per second per kilogram. That's how much energy per unit time per kilogram of rock you generate from the decay of radioactive elements. And of course, it correlates with the concentration of potassium, uranium, and thorium. Now, as the heat is being generated inside, you can kind of think that this heat is also going to dissipate out by conduction. So you might come up with a rough scaling, would be what is the temperature change. We might put the mass of the sphere times its specific heat. That's the change in total energy of that blob due to a change in temperature. And that's going to be related to the, I should actually put a approximate sign, the rates of total heat generation in there. And so that would be H, right, which is watts per kilogram, multiplied by the density, by the mass actually. So I have to take density times the volume, which is going to scale with R3. I'm going to drop the 4/3 pi because I'm just looking at orders of magnitude. So R3 is a volume term, density there, and so density times volume is mass. Mass times the heat production per kilogram now gives me the joules per second here. And so that's heat production. And it's going to lose heat by conduction. And we can think of that as, well, a negative sign because it's losing it. And it's going to lose it at a rate that's going to scale with the thermal conductivity. Note that this K is different from my kappa, which is thermal diffusivity. Note that K, kappa, which is this thing, is equal to K over density times the heat capacity there. So this is K. It's just Fick's law. And what we're going to do is we're going to have the temperature gradient between my blob and the surroundings. Again, we're only looking for orders of magnitude, but I could say, well, delta T is the temperature difference between the interior and the surroundings. And that operates over a length scale of about R right here. So K delta T over R is the heat flux. And we're going to have to multiply it by the surface area of the sphere, which is 4 pi r squared. And I'm going to drop the 4 pi again because, again, order of magnitude, so r squared. And we're going to consider a case when this is at steady state, okay, where the heat production is balanced by the loss of heat, and so the temperature of the blob is constant. And so this, we can say, is 0 there, and we equate these things here, and then what you will get is a delta T. Your steady state delta T is going to be scaling along the lines of this right here over K. So let's take a step back and see if this makes any sense. If H is very high, I have a lot of heat producing elements in there, of course, this thing's going to be hot. If R, or the size of it, is huge, it's again going to be hot because it'll be very difficult to get that heat out because it's so darn big. The surface area to volume ratio actually controls that. And again, the thermal conductivity matters. If the conductivity is very high, then you dissipate the heat, and so your steady state tends to be lower. Okay. Now all I have to do is then plug this delta Ts into here for that delta T, and then what I get is a different type of Rayleigh number, which we call the internally heat producing Rayleigh number, and that's going to be rho squared alpha G H R. Look at that, a 5 instead of a 3, the 5th power divided by kappa, eta, and K. It's a bit more complicated right here. And that, so here we have the bottom heated Rayleigh number. Here we have the internally heat producing Rayleigh number. And again, thermal expansion, of course, is important. Gravity is important. But here, if you have a lot of heat production, then the Rayleigh number will be higher as expected. Your intuition should tell you that. But instead of an R to the cubed, we have an R to the 5th power. That's simply because you have to account for the total mass of the uranium, thorium, potassium in your layer. So if you get a very thick layer, you really build up the heat production very quickly. So by the way, H is a heat production concentration, right? It's joules per kilogram. And so if you have a very thick layer, it can get very hot very quickly, and then you start to convect rapidly. So even more sensitive to size than the bottom heated system. And I leave it to you as an exercise to plug these numbers in to see what the Earth might be. Thank you.